Okay, here's a thought experiment for you. What if everything we think we know about reality, from the tiniest quantum particles right up to the scale of galaxies, what if it's all just surface level? What if it's emerging from something much, much deeper, something more structured? Imagine a universe where the fundamental constants, the numbers that seem to govern everything, aren't just arbitrary values someone dialed in, where forces aren't just there because they are, and where even the strangest quantum effects, the weirdness, actually makes perfect geometric sense. Okay, let's try and unpack this. This isn't just some incremental update to physics. It's presented as a radical inversion almost, a suggestion that reality isn't built piece by piece, but it emerges whole from a kind of pre-existing, maybe even intelligent coherence. Think of the universe like a symphony, and everything we observe, just notes played by this hidden, incredibly structured instrument. Welcome to the deep dive. Today we're diving into something ambitious, the unified coherence theory of everything, or UCTE for short. And look, this isn't just another theory trying to get noticed. It's framed as a really radical re-envisioning of reality itself. It offers this single, maybe elegant framework for everything. Quantum particles, cosmic structures, all of it. We've got some detailed briefing materials, a layered narrative explaining UCTE, its foundations, its implications, even how you might test it experimentally. So our mission today is to distill the really crucial insights from all that, help you, especially if you're a physicist, an inventor, or just an advanced learner in this space, quickly grasp what makes UCTE potentially, well, paradigm shifting.
It really is compelling. What's fascinating here, I think, is how UCTE tries to unify these fields we normally treat separately, quantum physics, atomic structure, cosmology, puts them all into one single model driven by resonance. It really challenges a lot of our standard assumptions. It offers this coherent, geometric, almost harmonic explanation for things we often just accept as fundamental or maybe even arbitrary. So we'll be exploring the what of it, definitely, but also the why it matters. Looking at the concepts, yes, but also trying to understand the rigorous ideas behind them and, importantly, those testable predictions. And for researchers listening, I mean, this could be huge. Imagine if we could finally ditch, dozens of arbitrary parameters we plug into models, if we see them instead as inherent design features of the universe, geometrically locked in by this fundamental vacuum structure. That changes everything.
All right, prepare for maybe some serious aha moments along the way. We'll dive into the theory's foundation, this thing UCTE calls the coherent vacuum. Then we'll explore the universal locks, sounds intriguing, that supposedly define our physical world. We'll see how UCTE reinterprets the, let's be honest, often baffling world of quantum mechanics. And then we zoom out, look at the potentially staggering technological possibilities and the actual experiments proposed to see if this whole thing holds water. It's a journey, really, to the core of what we think reality is. Okay, so if we're really going to deep dive into how UCTE reimagines reality, we have to start with its most, foundational claim, the coherence vacuum. The material states, pretty clearly, reality isn't built from particles and forces glued together by arbitrary constants. It emerges from a deeper, structured field called the coherence vacuum. Feels like a massive shift from how we usually think, doesn't it? So for our audience, many of whom, live and breathe quantum field theory, how does this coherence vacuum fundamentally differ from the standard quantum vacuum? The one with all the fluctuations. Why is that difference so critical here?
That's the perfect place to start because, yeah, the distinction is absolutely critical. The standard picture, especially in QFT, often paints the quantum vacuum as this sort of chaotic, turbulent sea. Random zero-point fluctuations. It's where virtual particles pop in and out of existence constantly like an energetic froth. It's messy, fundamentally random. But UCTE completely redefines this. It describes the coherence vacuum not as empty, random space, but as, and I'm quoting here, a structured resonance field with harmonic eigenmodes. It behaves more like a harmonic medium than empty space. So instead of chaos, UCTE sees this incredibly organized, active medium, a medium that literally provides the framework for physical reality. It's described as rich in potential energy and resonance patterns, so think less. Boiling pot of random stuff, and more like a perfectly tuned musical instrument, preset with specific frequencies, specific resonances, just waiting for reality to be played on it.
That's quite a claim. The vacuum isn't just nothingness or random noise, but it's dynamic, an active participant in creating reality. It sounds almost like a contradiction in terms. How do we even wrap our heads around something that's both a vacuum, empty, and yet has this rich, coherent structure inside it? What does UCTE offer to help us bridge that conceptual gap?
Exactly. And it does seem paradoxical at first glance. To give it more concrete form, the theory introduces something called the vacuum coherence tensor. This tensor is described as encoding how energy is distributed and how symmetries emerge from this vacuum. Now, for those of you who appreciate the math behind these ideas, think of a tensor not just as, a grid of numbers, but as a sophisticated mathematical object, a kind of multidimensional map. It precisely describes how energy and fundamental symmetries are organized within this vacuum structure. It implies there's a pre-existing coherent pattern from which everything else arises. You could almost visualize it like a crystal lattice, but for energy and information, not atoms. And this structured vacuum, it has inherent harmonic eigenmodes. These are essentially stable points, like attractors where reality kind of locks in.
Yeah.
These are like standing wave patterns that define where stable physics can even happen. They're like the preset resonant frequencies of that instrument I mentioned. A really profound shift away from seeing the universe as just assembled randomly. It suggests the very fabric of space guides stability and organization right from the start.
Okay, for the professionals listening, especially those working in theoretical physics where particles are usually seen as excitations of fields within a more standard vacuum, this is a huge conceptual leap. What does it actually mean for our understanding of fundamental physics if the vacuum itself, described by this tensor, is the generative source? What are the sort of practical implications for researchers and theorists working at the edge?
Well, this gets us to a really crucial point. If the universe genuinely emerges from the structured field, then the fundamental properties we observe, particle masses, force strengths, the value of constants like C or H, they aren't arbitrary. They can't be. They have to be direct reflections, manifestations of the vacuum's own inherent geometry and its resonance properties. This implies a deep underlying order that, let's face it, standard models often struggle to explain without just plugging in a whole bunch of free parameters, numbers we measure but don't derive from first principles. So for professionals, this offers a potentially unified explanation, a way to connect phenomena we currently treat as separate. It offers a possibly more elegant and maybe even more predictive framework. It suggests that many things we thought were just accidental features of our universe might actually be geometrically necessary, baked into the vacuum structure. This could lead to a massive reduction in the number of arbitrary constants physics relies on. We'd be moving towards a truly deterministic geometric universe where everything is connected, everything predictable. It's a shift from just describing the universe to actually explaining it.
All right, so we've established this dynamic coherence vacuum, and we see how it might set the stage for constants not being arbitrary. It's clear UCTE is really trying to rewrite the rules. And this next part, this is where it gets really interesting, I think. The sources explain that within this coherence vacuum, there are resonant eigenvalue thresholds, natural harmonic plateaus, and these supposedly stabilize everything we observe. Forces, constants, electron shells, maybe even time itself, they're called universal locks. What exactly are these thresholds? What makes them universal locks? How are they different from, say, the energy levels in an atom? Those are stable states too, right?
Yeah, they are stable states, but the difference is key. These thresholds are described as discrete coherence points where the vacuum itself locks into stability. And that's what gives rise to the fundamental properties we see everywhere. They're called signatures of where the vacuum locks into stability. The crucial distinction from something like atomic energy levels is their universality. Atomic levels belong to specific atoms. These UCTE thresholds are proposed as fundamental properties of the coherence vacuum itself. They underlie all physical phenomena. They aren't just values. They represent these stable, fundamental configurations of the harmonic medium. Like the specific notes a perfectly tuned crystal or instrument can produce, think of them as universal resonant sweet spots, places the universe prefers to settle into, dictating the rules of the game across all scales. They are the fingerprints of vacuum resonance, explaining why things are stable, why they have the precise properties they do from electromagnetism's strength to an electron's charge.
The briefing documents give some concrete examples of these universal locks. Can you walk us through how these actually show up in the physics we know? Because it's one thing to talk abstractly about thresholds, but seeing the connection to familiar measurable physics really helps ground it, especially for, an engineer or a physicist listening.
Absolutely. And tying it to known physics is essential. The theory identifies several critical thresholds, each linked to a fundamental aspect of reality we work with every day. First, there's U1. This threshold is said to stabilize electromagnetism. And crucially, the fine structure constant, alpha, that number, about 11,137, that dictates the strength of EM interactions. The source specifically mentions this U1 lock helps explain why hydrogen atoms are stable, pretty fundamental. Usually alpha is just a number we measure. Here it emerges from a fundamental vacuum lock.
Okay, so alpha isn't just a constant, it's a result of this lock.
Exactly. Then there's SU2. This one locks spin-phase topology and weak force symmetry, and it stabilizes the weak coupling constants involved in radioactive decay. It's presented as crucial for understanding that weird 720-degree rotation needed to return a spinor like an electron to its original state, something that's always felt purely mathematical.
Right, the 720-degree thing, always a mind bender.
UCTE says it's a direct consequence of this SU2 vacuum lock. It's geometry, not just abstract math. And finally, there's SU3. This one governs the strong nuclear force, nuclear binding, quark confinement, why protons and neutrons stick together in nuclei, why hadrons are stable. It explains the cohesion of atomic nuclei, basically stopping the universe from dissolving into quark soup. Each of these thresholds offers a deep geometric reason for things we often just take as given constants or rules. They're shown as inherent properties of reality's deep structure.
Now, what gets really exciting, especially for advanced learners or researchers, is when a theory makes predictions. Goes beyond just explaining what we already see. UCTE talks about SU4+, and potentially even higher plateaus. This is where it stops just explaining and starts generating potentially new knowledge. What might these higher locks reveal? What impact could that have on fields like material science or high-energy physics?
Yes, this is where the theory really becomes generative looking forward. UCTE explicitly predicts entirely new stability bands beyond the known SU3 threshold. These higher plateaus, SU4 and perhaps beyond, are expected to govern the existence and properties of things like superheavy elements and maybe exotic electron shells we haven't conceived of. This isn't just about adding a few more boxes to the periodic table. It potentially opens up entirely new stability bands for material science and chemistry.
So new stable elements way beyond what we know.
Potentially. Imagine designing elements or compounds with properties we can't even imagine right now. Super dense, incredibly stable new materials. Elements with completely novel chemical behaviors, all based on understanding these higher vacuum locks. For researchers in nuclear physics or advanced materials, this isn't just explanation, it's a potential roadmap to discovery. It predicts what we could find and where to look. It's a powerful claim about the predictive power here, guiding experiments towards genuinely new frontiers.
So this really loops back to those fundamental constants like the speed of light, Planck's constant, the electron's charge, the numbers that have always seemed so specific, so finely tuned. It sounds like UCTE is saying they aren't random numbers we just have to accept and plug into equations. They have a much deeper intrinsic origin. That would finally address that whole fine-tuning problem, wouldn't it?
Precisely. That's the core idea. The theory posits that physical constants arise from geometry, their fingerprints of vacuum resonance. They are not arbitrary values we just happen to measure. They emerge directly, necessarily, from these specific resonant eigenvalue thresholds, these universal locks within the coherence vacuum. This offers a unified geometric explanation for why they have the exact values they do, which, as you say, has been a huge, long-standing puzzle and source of debate in physics. Why these numbers and not others? Instead of parameters that need fine-tuning, UCTE presents them as intrinsic properties reflecting the vacuum's underlying structure. For physicists, that's a monumental conceptual shift. Moving away from a universe that seems to have arbitrary dial set just right, towards one where these fundamental values are elegantly, maybe even inevitably, determined by the geometry of reality itself. It makes the universe feel much more coherent, more understandable at its base. It potentially dissolves the fine-tuning problem by suggesting the universe is inherently structured this way.
It's pretty remarkable how UCTE aims to reframe something as basic as physical constants. Now, speaking of fundamental properties we thought were just inherent, UCTE also offers a profoundly different way to look at one of quantum mechanics' most famously weird concepts, particle spin. Quantum spin is often taught as this intrinsic property, like a tiny top spinning, but we know it's not really classical rotation, it's just spin. How does UCTE tackle spin? Does it offer a more intuitive way to understand it, something beyond just accepting it as a quantum postulate?
That's a fantastic question because spin has always felt a bit mysterious, hasn't it? A property without a clear classical analog. What's fascinating is UCTE's redefinition. The theory states, spin isn't an intrinsic property, but the projection of hidden geometric planes called bivectors. Okay, what does that mean? Instead of being some inherent fuzziness a particle just has, spin is viewed as the projection of these internal rotations into observable vectors.
Okay, hold on. Bivectors, hidden geometric planes. Can you unpack that a bit?
Sure, think of it like this. Imagine a really complex gyroscope spinning in more dimensions than our familiar three. A bivector represents a plane of rotation in this higher dimensional space. What we perceive and measure as spin in our 3D world is just the shadow or the projection of that deeper, more complex internal rotation onto our reality. The source material even gives a specific rotor equation with 4-periodicity involving math like 3 fata, leading to the spin vector math BFS. Now, without getting lost in the specific equations like 3 fat the crucial point is that spin's weird 4 or 720-degree periodicity, that signature feature of electrons and other spin 12 particles, emerges naturally from this geometric picture. It's not an extra rule we had to add, it's just how projections from these bivector rotations work. It provides a potentially more intuitive, visual, yet mathematically grounded way to see spin as a consequence of hidden geometry.
And how do we actually measure something that's just a projection of some hidden geometry? Measurement in quantum mechanics is already famously problematic, tied up with wave function collapse. The sources mention something called the asymmetry resonance operator, or ARO. How does this operator connect that hidden geometric reality to the definite, discrete outcomes, spin up, spin down, that we actually see in experiments?
Right, that's a critical piece for any theory trying to reinterpret quantum measurement. UCTE proposes that measurement involves this asymmetry resonance operator, ARO, and its role is to collapse the bivector plane, producing discrete outcomes. And again, for those who like the mathematical details, the source provides a specific form for this operator. What this mathematical tool essentially does within the UCTE framework is interact with that underlying geometric bivector plane. It forces it to align or project in a specific way relative to the measurement axis represented by A. This interaction is what yields a definite classical-like result like spin-up or spin-down from what was initially a purely geometric quantum state. So it's not just a concept, it's presented as a calculable mechanism for how we get discrete quantum measurements from this underlying geometry.
Speaking of quantum mysteries, let's talk entanglement. Einstein famously called it spooky action at a distance, that seemingly instantaneous correlation between distant particles. It's always been one of the most counterintuitive parts of quantum theory. How does UCTE approach this? It suggests it's more about coherence preservation rather than some kind of faster-than-light signaling. How does that work, and how might it simplify things? This seems crucial for anyone working in quantum information.
It absolutely is crucial, and it touches on the very nature of locality and reality. UCTE offers a fundamentally local and geometric take on entanglement, aiming to completely remove the spookiness. The proposal is, 2 entangled spins share a single bivector plane. Remember those geometric planes underlying spin. In entanglement, 2 particles share the same plane initially. Then, measurements splitting the plane into correlated projections. When you measure one particle, you're essentially forcing a specific projection of that shared plane. Because the other particle is still linked to that same original plane, its projection is instantly correlated, but not because information traveled between them. The key insight is Bell correlations emerge geometrically, not via spooky action. It reframes entanglement not as instantaneous communication, but as a consequence of this shared internal geometry. The coherence, the link, was there from the start.
So it's like tearing a single geometric object in two. The pieces are intrinsically related because of their shared origin.
Exactly. Imagine 2 pieces of a torn photo. They match perfectly along the tear, not because they're communicating, but because they were once part of the same whole. Their correlation reflects their shared history, their shared geometric origin in this bivector plane. UCTE suggests this provides a more intuitive, unified, and crucially, local understanding. It resolves the paradoxes by making entanglement a property of shared foundational coherence embedded in geometry rather than mysterious FTL signaling. This could have huge implications for how we think about quantum information transfer and computation.
Okay, moving up a scale now, from subatomic quantum weirdness to atoms themselves. UCTE claims to explain something absolutely fundamental to chemistry and materials science: electron shells and the entire structure of the periodic table. It suggests these aren't just emergent properties of quantum mechanics and electromagnetism, but direct manifestations of the coherence vacuum's resonant structure. That's a huge claim, connecting the deep vacuum structure to the organization of all matter. How does that connection work? What's the proposed mechanism linking vacuum harmonics to stable atoms?
Yes, this is where UCTE really tries to bridge the gap between the fundamental vacuum and the matter we see. The theory posits that electron shells stabilize at standing wave attractors tied directly to eigenvalue harmonics. What that means is the stable configurations of electrons orbiting a nucleus aren't just due to the push and pull of electric charges, the Coulomb forces we learn about. They're fundamentally linked to the underlying resonant structure of the vacuum itself.
So the vacuum provides the allowed spots for electrons.
In a sense, yes. It's not just electrons finding minimum energy states based on attraction to the nucleus. It's more like the vacuum itself provides specific slots or resonant frequencies, these standing wave attractors where stable electron configurations can exist. The stability of these shells, why we have distinct shells like K, L, M, and their specific electron capacities to 18, is said to be directly tied to the harmonics tied to eigenvalue thresholds, those universal U1, SU2, SU3 locks we discussed earlier. This provides a potentially deeper, more fundamental reason for why electron shells exist and have the structure they do. It aims to move beyond just describing the rules, like the Pauli exclusion principle or Hund's rules, to explaining their origin in the vacuum's own structure. It's a very unifying concept.
So if I'm getting this right, the very organization of matter, the periodic table that hangs in every chemistry lab, isn't just a useful way to classify elements based on electron configurations. It's actually a direct reflection of this deeper vacuum structure that would imply the periodic law itself. The fact that chemical properties repeat periodically isn't just an empirical observation, but it's mirroring the universe's fundamental geometric or harmonic architecture.
Precisely. That's the assertion. Periodicity in the periodic table reflects vacuum structure, not arbitrary Coulomb interactions. It provides a foundational explanation for why atoms are stable in the ways they are and why matter organizes itself into the elements we see. And what's really fascinating, especially for professionals in chemistry or materials science, is that the theory then says, okay, if SU3 explains the known periodic table, what about SU4 and higher? It predicts new stability bands and exotic chemistry beyond SU3, directly linked to those higher eigenvalues. This suggests the periodic table we know might just be one part, one octave perhaps, of a much larger organizational principle determined by the vacuum.
Like undiscovered islands of stability for superheavy elements.
Exactly. Potentially whole new rows or blocks in the periodic table, corresponding to these higher SUN locks, hosting elements far heavier than anything synthesized so far, and perhaps exhibiting completely novel chemical properties. For chemists and material scientists, this isn't just theory, it's a potential guide to discovering entirely new elements and compounds. Maybe room temperature superconductors, maybe materials with unbelievable strength-to-weight ratios, all potentially predictable based on the vacuum's harmonic principles. It could fundamentally reshape synthetic chemistry and materials design.
Okay, one of the things that really distinguishes a potentially groundbreaking scientific theory from just, an interesting idea is its ability not just to explain what we already know, but to predict new things and, crucially, be testable. UCTE is explicitly presented as generative, predictive, and testable. What does that actually mean in practical terms? Especially for our listeners, the professionals who might be looking for new research directions, innovation opportunities, maybe even investment targets.
Right. This is absolutely where the theory has to deliver, where the rubber meets the road. So let's break that down. A generative theory provides a mechanism, an underlying engine that produces the phenomena we see. It explains how things work from deeper principles rather than just describing them. A predictive theory anticipates new observations, things we haven't seen yet but could look for. And a testable theory offers clear, concrete ways to perform experiments that could either confirm or, just as importantly, refute its claims. UCTE aims to be all three. It's not intended as just a philosophical framework, it's designed to be put to work. It suggests profound technological possibilities and lays out specific experimental paths to check its validity. So for professionals, this means UCTE isn't just a different way to think about the universe. It's presented as a potential blueprint for revolutionary new technologies and a fertile ground for experimental discovery, pushing well beyond current limits.
That sounds incredibly compelling. Let's dig into some of those transformative applications then. The briefing materials sketch out several really intriguing possibilities that could genuinely reshape technology, from computing to energy to materials. What are some of the standout examples? What could we actually do if this understanding of reality is correct?
Okay, thinking about the potential impacts, quite broad. First, consider quantum coherent devices. A major hurdle for quantum computing now is decoherence qubits losing their quantum state too quickly. UCTE predicts that if you could align qubits with vacuum eigenmodes, you might achieve near-zero decoherence.
Near-zero decoherence, that would be revolutionary.
Absolutely. It could mean significantly longer coherence lifetimes, potentially orders of magnitude longer. That unlocks the door to truly powerful, stable quantum computers capable of tackling problems far beyond anything possible today. Second, vacuum energy harnessing. This one sounds like science fiction, but the theory suggests the ability to modulate resonant locks for energy exchange. The idea is if you could match field geometries to these specific vacuum resonance thresholds, you might unlock ways to extract energy directly from the vacuum structure.
Wow. Clean, limitless energy.
Potentially. It suggests pathways for entirely new energy technologies, possibly moving beyond fossil fuels, renewables, even nuclear, towards something fundamentally different. A huge if, obviously, but the theoretical possibility is there. Third, material discovery. We touched on this with the higher SUN locks. UCTE's predictions of super heavy stable shells in exotic crystal phases could completely change materials science. We might be able to discover or even design from first principles materials with properties we currently consider impossible. Super hard, ultralight alloys, room temperature superconductors, materials based directly on optimizing interaction with vacuum harmonics. This could transform aerospace, electronics, medicine, everything. And finally, maybe the most far-out idea. Intelligent systems. This looks way ahead. It's the idea of AI and human cognition aligned with substrate-level coherence, leading to cognitive technologies operating at substrate speeds.
Okay, what does that even mean? AI running on the vacuum.
It suggests a new paradigm for AI, perhaps moving beyond silicon. Maybe AI that operates at a much deeper, more fundamental level of reality, directly leveraging the universe's inherent coherence. It hints at forms of intelligence or computation that could interact with the universe in ways we can barely conceive of now, truly transformative if realized.
Okay, these are definitely paradigm-shifting possibilities, but for the researchers and scientists listening, predictions are only as good as the ability to test them. A theory this radical needs a solid experimental roadmap. What specific, concrete experiments are actually proposed to check if UCTE holds up? How do we go about validating these claims about vacuum structure, bivectors, and universal locks?
Right, and the theory doesn't just make vague promises. The materials outline specific, measurable, experimental approaches. First, to directly test for those predicted higher stability bands, UCTE proposes detecting SU4 plus eigenmodes using techniques like high-resolution spin resonance spectroscopy. You'd be looking for very specific energy absorption or emission signatures that correspond to these predicted new vacuum states. Second, related to that, you can probe predicted shell stability bands through superheavy element synthesis. This means pushing experiments at places like particle accelerators to create elements far heavier than oganesson, element 118, and studying their properties very carefully. Do they exhibit unusual stability or chemical behavior consistent with SU4 plus predictions?
So looking for those islands of stability directly.
Exactly. Third, to test the geometric interpretation of entanglement, the proposal is to test entanglement coherence splitting predictions using systems like NV-center qubits. For listeners, NV-centers are nitrogen vacancy defects in diamond crystals. They're a really well-controlled platform for quantum experiments. These experiments would be designed specifically to see if the correlations match the geometric splitting model rather than requiring non-local explanations. And finally, to really pin down the fundamental nature of the vacuum itself, researchers could try to confirm vacuum resonant thresholds directly using spin-based interferometry. This involves using the spin of particles in highly sensitive interferometers to measure how they interact with the vacuum, looking for evidence of these discrete resonance points. So it provides a clear, actionable experimental program. Physicists can actually design and run these experiments to engage with UCTE's core claims and potentially confirm or falsify them. It moves it out of pure theory and into the lab.
We have covered a huge amount of ground today. Wow. From the coherence vacuum as the source of everything, through these universal locks setting the rules, reimagining quantum spin and entanglement geometrically, right up to predicting new elements and potentially intelligent systems. It's really clear that UCTE isn't just adding a few details to physics. It's proposing a fundamental rewrite of our core concepts. It challenges assumptions many of us have probably held since university.
Absolutely. If we just zoom out for a second and recap the biggest shifts UCTE proposes, it really is a comprehensive reframing. Constants become resonance locks. They're not arbitrary, they're geometric necessities of the vacuum. Spin emerges from hidden geometry. It's not just an intrinsic quantum number, it's a projection of deeper rotational structure. Forces arise from phase lock thresholds. They have a unified origin in how different aspects of the vacuum coherence lock together. And shells are harmonics of the vacuum. Atomic structure directly reflects the vacuum's resonant frequencies.
Yeah, it's not just about finding new answers to old questions. It feels like it's prompting us to ask entirely new questions about the universe and how it's put together.
Yeah.
It really is pitched as a paradigm shift. But, Any theory proposing such a radical overhaul must face some pretty significant hurdles, conceptually, experimentally. What are some of the immediate challenges UCTE might face in gaining traction, even among an advanced audience like ours?
That's a very fair and crucial question. No paradigm shift happens easily. One huge hurdle is simply the conceptual leap required. Physicists have decades of intuition built around the Standard Model, quantum field theory, particles as fundamental, the vacuum as fluctuating, but maybe not structured in this way. Overcoming that inertia is massive. The mathematical framework, while presented as rigorous, is also novel. It requires physicists to learn new tools, new ways of thinking about geometry and resonance at this fundamental level.
So a steep learning curve.
Definitely. And experimentally, while specific tests are proposed, they are hard. Detecting subtle SU4 plus resonances, synthesizing and characterizing superheavy elements that might only exist for fractions of a second, measuring vacuum properties with interferometry at unprecedented precision. These push the absolute limits of current technology or maybe require new tech altogether. And then there's the challenge of integration. The Standard Model is incredibly successful empirically. UCTE needs to show not only how it explains things the Standard Model doesn't, but also how it recovers all the successes of the Standard Model within its framework. Where do they align? Where does UCTE extend or replace it? That's complex theoretical work. It really challenges us to re-examine what we mean by fundamental, and it forces us to look for connections, maybe hidden geometric connections, that our current frameworks might obscure.
Okay, we've taken a really deep dive today into the unified coherence theory of everything. We've explored this idea of universe emerging from a structured coherence vacuum, a place where constants are fingerprints of vacuum resonance, not just numbers, where quantum mysteries like spin and entanglement might have elegant geometric roots. We've seen how UCTE presents itself as generative, predictive, and testable, with implications that could ripple through quantum tech, material science, AI, energy, potentially everything. It's a theory that clearly doesn't just aim to explain, it aims to inspire a whole new way of seeing.
And what's truly fascinating, I think, is the implication if UCTE, or something like it, proves correct. It implies an intrinsic order, a deep coherence to the cosmos that's far more profound and interconnected than we maybe currently imagine. It suggests the universe isn't just a collection of random parts governed by accidental laws, but something deeply resonant, geometrically determined. So maybe the provocative thought to leave you with is this. If the universe really does operate on these fundamental harmonic principles rooted in geometry, what other hidden geometries, what other resonant locks might still be out there waiting to be discovered? And what further layers of reality could this deep coherence unveil if we learn how to perceive them? What else might be hidden just beneath the surface?